Okay, so we are in the context of continuum mechanics, where we consider a linearly elastic material whose reference configuration is omega, an open bounded set of Rn, and we apply a deformation to the material. Here we are in the context of linearized elasticity. So we assume the deformation is small, so that the kinematic quantity, which is substantial, is the vector field displacement u, so that the deformed material is identity plus u of omega. In this talk, I will consider dissipative phenomena where the elastic properties of the material will be altered on some regions of the material. So I will organize this presentation in 3 parts. First, I will introduce the general context of brittle damage and the typical total energy associated to this model. And in a second part, I will motivate the question in the title with a static analysis where Babajan, Yolano, Rindler have shown how, by adding a small parameter inside the brittle damage energies, they can recover in the limit, as the parameter tends to 0, a model of Hencky plasticity. So this is in the static setting, and this motivates the question, can we extend this analysis for a quasi-static evolution in time? So quasi-static means that I will neglect the effects of inertia. Okay, so in the general context of brittle damage, we make the assumption that the material exists only in 2 different states. It means that at each point of the reference configuration, we are either in a region where we have weak material, damaged material. It means that the elastic properties are less, they are altered. Or we are in a sound region where we have sound material and the elastic properties of the strong material are not altered. The elastic properties of these 2 phases are represented by 4th order symmetric tensors, the rigidity tensors, which satisfy this ordering property in terms of quadratic forms acting on the symmetric matrices. So it means that the rigidity of the weak material is less than the rigidity of the sound material. Classically, to describe dissipative phenomenon, it's natural to introduce an internal variable which will encode, which will describe the state of damage of your medium. And since here we are with a brittle material, which exists only in 2 possible phases, a natural internal variable is the characteristic function of the damaged regions, which I call chi. So here, chi, the characteristic function of the damaged regions, and the displacement u are variables of the model. And so here I follow a model introduced by Francfort and Marigo, which consists in defining the total energy associated to such a couple u and chi as the sum of 2 terms. Here you have the elastic energy stored in the medium, because you recognize here the rigidity tensor of our material. When chi equals 1, we are in the weak regions, so we have the rigidity of the weak material. And when chi equals 0, we are in the sound regions, where we have the rigidity of the strong material. E of u is the linearized elastic strain, because we are in the context of linearized elasticity. It's only the symmetric part of the gradient of the displacement u. And here you have a dissipative term, which penalizes the existence of the damaged regions. So this is, their model consists in saying that the pay to cost for having damaged some regions is taken as proportional to the volume of the damaged regions, so the integral of chi, multiplied by kappa, which is the toughness of the medium, which is a positive parameter. Here there is no time, we're in a static setting, and the grounding assumption is that the material will try to reach an equilibrium configuration which corresponds to minimum for the total energy. But, well, we have a lack of convexity in 1D and symmetric quasi-convexity in the general vector setting. So the problem is ill-posed. So first, if you fix U, you can see that this density is always greater than either this term or this term, since chi is either equal to 0 or 1. Of course, the density is greater than the minimum of these two values, which I call W, and it's a minimum between two quadratic functions, but one is translated vertically, so you see with this draw in 1D that this is not convex. So we need to relax the energy, and the relaxed energy is given by the symmetric quasi-convex envelope of the density W, or the convex envelope in 1D. Okay? So this symmetric quasi-convex envelope is given almost explicitly thanks to the Hashing-Strickman bounds, which express it in terms of a minimization problem taken among all homogenized materials in the G theta set. So let me explain what happens here. What happens is that minimizing sequences will find energetically favorable to develop microstructures in a layered way. So it will develop layers alternating between weak and strong materials, and as the minimizing sequence will converge, the scale of the layers will tend to 0. So in the limit, we lose the brittle character of damage, and we come into the world of progressive damage, where we obtain all possible homogenized material between weak and strong phases, fine mixtures between these two. So this is a phenomenon of homogenization, which appears here. By relaxing the energy, we enlarge the set of admissible materials, and now any homogenized material is admissible. It means that when you take a point of the reference configuration, you have a volume fraction of weak material and 1 minus theta of strong material. In 1D, the G theta set reduces to a single point. And so this is explicit, and indeed you can see in 1D that we know explicitly the convex envelope. This will be important for the third part. So now let me motivate the question by a static analysis led by Babajan, Irlano, Rindler, which, so what they did is that they introduced a small parameter, epsilon, inside the brittle damage energy, and by doing so, they modelize two phenomena which will occur in competition simultaneously. The first one is the elastic degeneracy of the weak material. As you can see that the rigidity of the weak material is multiplied by epsilon. So when epsilon go to 0, you tend to total damage. On the other hand, here, they force the concentration of the damaged regions, because if you consider sequences U epsilon, chi epsilon, for which the total brittle damage energies are bounded, since kappa over epsilon diverges, you must have that the integral of chi epsilon converges to 0. So the volume of the damaged regions converge to 0. And what they have proved is that this scaling law is a non-trivial one, which leads, asymptotically in terms of gamma convergence to an energy which is typical of Hencky plasticity. So I won't give a complete definition of Hencky plasticity. I will just stress out important features. So the effective energy takes finite values for vector field displacement u, which has bounded deformation and for which there is an additive decomposition of its strain, so its symmetric gradient, which is a radon measure, into two terms. One term which will account for the elastic, the reversible part of the deformations. So we will call this part the elastic strain, E. And the second part will account for possible permanent deformations that might occur. And we call, therefore, this part of the strain, we call it the plastic strain. You can see that the total energy is defined as the elastic energy stored in the medium, which is expressed only in terms of the elastic strain. And here you have a dissipative term expressed in terms of the plastic strain. I do not give a formula for this because in 1D it will be explicit, okay? But this density for the dissipative term is the support function of some convex set K, which is explicitly known here, but I do not give details. And what is the meaning of this convex set K? When the strain takes values in the interior of the convex set, no plastic deformations can occur. So the interior of the convex set K is called the domain of elasticity. Plastic deformations can occur only when the strain reaches the frontier, the boundary, sorry, of K, which is called the yield surface. Okay, so this is in a static setting, and now the question is, can we do the same by adding times in the simplest evolution setting, which is quasi-static evolution, where we neglect inertia? So it was a difficult question, and 2D was too difficult, so here I restrict to the one-dimensional. So the medium lies on the real line, and the reference configuration is the segment 0, 1. The rigidity tensors are now scalars. A weak for the weak material, and A strong for the sound material. Okay. So I didn't give many explicit details in the vectorial setting, because in 1D everything is explicit, so I just recall the result in the static setting. Babbage-Jorlano-Rindler's scaling law injected in the brittle damage energy of Francfort and Marigo leads to Hencky plasticity. Here, the convex set of plasticity is simple. It's just the segment minus square root of 2 kappa A weak square root kappa A weak, and in this case, the support function simply is this. So the dissipative term is explicit here. Okay, let me reformulate the question once more. Can we inject the scaling law introduced by Babbage and Jorlano-Rindler into a notion of quasi-static evolution of brittle damage? And when we do the asymptotics, when we let epsilon tend to 0, do we recover a quasi-static evolution of perfect plasticity as defined by Salmazo, De Simone, Moa? So here, this is not a result about existence, which is already done. The question really is, can brittle damage lead to plasticity? What I will do next is explain to you what is the quasi-static evolution of brittle damage introduced by Francfort and Garroni. What they do, okay, so in a quasi-static evolution, the grounding assumption is that your material at each time will seek to reach an equilibrium configuration. It will seek to minimize the brittle damage energy. In the first slide, I told you that the energy had to be relaxed and a homogenization phenomenon was occurring. What they do is that they subdivide the time interval. At the initial time, they minimize the relaxed energy with weak phase epsilon A weak and strong phase A strong. They obtain a first homogenized material and they pass to the next discrete time. They want to do the same, but they want to take into account the history of damage, which is irreversible. So now they do not have the sound material anymore at hand. They only have the previous homogenized material. So they do the same. They minimize the relaxed brittle damage energy with weak material and the previous homogenized one. And they go on. They let the time step tend to 0, and they obtain the following quantities that I will describe. I forgot to say that here I impose no volume force load on the medium, but I impose a Dirichlet boundary condition at the endpoints. Okay, so Francfort Garroni, directly coupled with the scaling law, gives you 3 quantities. A displacement, U epsilon, capital theta epsilon, which is the volume fraction of sound material at time t point x, because you have a homogenization, so you recover only a mixture. So, this density is decreasing in time because damage is irreversible. You have less and less sound material in proportion. And you have the rigidity of the material, which, because we are in 1D, is explicitly given in terms of the 2 phases and the volume fraction of sound material. This is also decreasing in time. It means, indeed, that the elastic properties of your material is decreasing. It's altered. Okay, they satisfy, in particular, the 3 following properties. First, the Dirichlet condition is strongly satisfied at all time by the displacement U epsilon. Next, this is a consequence of what they call the one-sided minimality, but in 1D in particular, what you get is that the derivative in space of the stress here is 0. So this is a function which doesn't depend on space. And we have the energy balance, which tells you that the total energy at time t, which is the elastic energy stored in the medium at time t, plus the dissipative cost for having damaged the proportion 1 minus theta epsilon of material. Okay, because this is the volume fraction of weak material at time t point x. This total energy is equal to the energy at the initial time plus the work of the forces, which is expressed with the Dirichlet boundary condition. The question is, can we pass in some sense to the limit epsilon goes to 0, and do we recover an evolution of plasticity? So in plasticity, as you've seen, what happens is that the strain is decomposed additively into an elastic part and a plastic one. So a part of the game is to understand at fixed epsilon what will play the role of the elastic and plastic strains. To do so, we just use these two facts. So I said that the stress, sigma epsilon, is homogeneous in space. It doesn't depend on space, it's only a function of time. Okay, and in particular, the derivative of u epsilon is equal to the stress times the compliance, the inverse of the rigidity, which is explicitly known, and you can see that you naturally have an additive decomposition with one term which depends on the volume fraction of weak material and one term which depends on the volume fraction of sound material. So these are natural candidates for the elastic and plastic strain at fixed epsilon. Okay, now we want to pass to the limit, so we need compactness, so we need bounds, and it turns out that we can prove the total energy is uniformly bounded with respect to time and epsilon. In particular, when you introduce this measure, which is non-negative and increasing in time, so this is a volume fraction of weak material at time t, rescaled by epsilon against the Lebesgue measure. These Radon measures are uniformly bounded, uniformly with respect to time and epsilon. And they are non-decreasing in time because the volume fraction of sound material decreases. So here we can apply Elise theorem, which allows us to take a subsequence in epsilon independent of the times. So along the same subsequence for all the times, we get that the Radon measures mu epsilon weakly converges to a limit non-negative Radon measure, which is still non-decreasing in time. We can also prove that we have pointwise convergence along the same subsequence at all time of the stresses to a limit stress, which I call sigma of t. With these two convergences, we obtain the convergences of the plastic strain at epsilon fixed and the elastic strain at epsilon fixed. So P epsilon weakly star converges to a limit plastic strain, which is given in terms of sigma, the stress, and mu, the limit measure. Here you have a strong convergence in L2 of the elastic strain to a limit elastic strain E, which is also given in terms of sigma. And we can also prove that the displacement weakly converge in BV to a limit displacement. What is remarkable here is that these are our candidates for a plastic evolution. I've done nothing yet, only a compactness result. But already at this stage, we can prove that all the quantities are absolutely continuous in time, which is something we obtain as a byproduct of being an evolution of plasticity. Okay, so this is nice. This is nice. Okay, so now what I'm going to do is tell you what our candidates satisfy, and in the same time, I will define what a plastic evolution is, quasi-static evolution of plasticity. So first, these four quantities describe a quasi-static evolution of plasticity if you have the additive decomposition of the strain, so the derivative of the displacement, into an elastic strain and a plastic strain. This is granted here because we defined P epsilon and E epsilon thanks to the additive decomposition at fixed epsilon. So of course this is still true in the limit. Second requirement is the constitutive equation, which tells you that the stress is linearly proportional to the elastic strain, and indeed this is granted by definition of my limit elastic strain. So we have the constitutive equation. Next, what happens for so in a plastic behavior, permanent deformations can occur until the boundary of your material, and the plastic strain will measure in some sense, how far your displacement is from the Dirichlet condition you wanted to impose. And I do not prove it, but indeed, we can prove that this limit plastic strain satisfies the required relaxed Dirichlet boundary condition. Then they must satisfy the equilibrium equation. So here there is no volume force load. We are in quasi-static, so we neglect inertia. The equilibrium equation just says this, which is true because sigma epsilon was only a function of time. So it's the same for sigma. It's only a function of time, constant in space. So we have the equilibrium equation. Then the stress must satisfy a constraint. It must live into the convex set K, which is explicit in 1D. And indeed, I do not prove it here, but believe me, the limit stress sigma indeed lives inside the convex set K. There is a last property to be satisfied in order for these four quantities to describe plastic evolution. This is a flow rule. Here, we have something which is due to the existence of the limit measure mu, which is not classical for a plastic evolution. And this is an evolution law on mu, which tells you that mu can increase only when the stress saturates the constraint. This is an evolution law on mu. And what we want to check is, do we have an evolution law for the plastic strain, which is the flow rule? If we have that, indeed, our candidates are describing a quasi-static evolution of plasticity. The flow rule means that plastic deformations can occur only when the stress saturates the constraint. So I will skip the proof and just tell you that the flow rule is equivalent to this situation. So here you have the Dirichlet boundary condition evaluated at the endpoints of the segment. Okay? So this condition reads as follows. You have an explicit threshold expressed only in terms of the data of the model, such that as long as this quantity lives under this threshold, it does whatever it wants. But as soon as this quantity strictly goes beyond this threshold, then for all the remaining times, it must be increasing in time. So here, this is unsatisfactory because, okay, for such good Dirichlet boundary conditions, indeed, as conjectured, we have a plastic behavior. But if I take a bad Dirichlet boundary condition, which doesn't satisfy this condition, we know that the flow rule is not satisfied, and we know that the limit, the effective evolution is not of the plasticity type. So this is an example of non-commutativity between the homogenization process, the gamma convergence, which was true at the static setting, and the evolution in time. So just to conclude, because I think my time is up. Just to conclude, in any case, actually what we've shown is that the limit effective behavior is one of damage. So we've shown that brittle damage leads to damage. Okay, so why? From the additive decomposition and from the fact that the plastic strain and the elastic strain are expressed in terms of sigma and mu, we have this constitutive equation here, which is one of damage in the sense that the stress is proportional to the strain we factor the inverse of this term if if it was legal to inverse it. This is interpreted as a compliance, inverse of the rigidity. The compliance is increasing in time. It means, indeed, that the rigidity is decreasing in time. This is typical of damage. And the evolution law we had on mu is, of course, true for the compliance because this is a constant measure in time. So here, what we have actually is a Griffith-type evolution law, which tells you that the rigidity of our material can decrease only if the stress saturates the construct. And even when we have the validity of the flow rule, it's a misunderstanding to read the effective evolution as one of plasticity. We can see this with a loading-unloading cycle where you stretch the Dirichlet boundary condition is just a stretch and it goes back to its initial configuration. So in our effective model, everything is explicit and the response of the material describes a cycle. It means that it goes back to its initial shape, and this is typical of damage. Whereas in plasticity, you expect to have a residual permanent strain, which we do not have. So even when the flow rule is true, which means we stop at this point of the cycle, so you have hidden the fact that it's not plasticity. Even when you have the flow rule, this is not plasticity, this is damage. Thank you for your attention. First, I was trying to prove something that was wrong. Maybe if I try it again in a higher dimension, not trying to prove something wrong, maybe I wouldn't have so much problems. But okay, the differences are that it's only the divergence of the stress, which is equal to 0, so you do not have homogeneity in space anymore, which was very useful in order to let the stress go out of the spatial integrals. It was useful for compactness reasons. You also do not find that easily. Actually, I didn't found that the limit stress. Okay, first, do we have a limit stress in the vectorial setting? Is it properly defined? And does it live in the convex set of plasticity K? This is difficult to, I don't know how to obtain that. It would be true for a scalar model where you take a full gradient with u, which is taking scalar values. Because in this case, the symmetric quasi-convex envelope is also the convex envelope, and I can obtain still the bound on the limit stress. And these are the two difficulties I have.